In this lecture, we're going to extend our discussion of correlation into something referred to as the coefficient of determination. And this approach will take a more predictive approach in examining the relationship between two variables. And specifically, the coefficient of determination is part of the process in which we wish to measure the proportion of the variability of one variable that's determined from the relationship with the other variable. And this, of course, is based on the magnitude of the Pearson correlation statistic, which is the R statistic. Now, if we take the computed R statistic, the Pearson correlation coefficient, and we simply square it, so we multiply it by itself, we arrive at the coefficient of determination. And this represents the explained, or what's often referred to as the common variance. We know that the prediction is not going to be perfect, and so what we want to do is work towards determining the variability that we can expect in making a prediction. So just a couple of notes with the coefficient of determination before we move on. The raw scores will deviate vertically, and when I use the term vertically, we're referring to the scatter plot, and we'll see the examples of the scatter plot and the coefficient of determination in this lecture. And so the raw scores will deviate vertically from the regression line or the line of best fit. But the big question that we ask in this approach is, how much will it deviate? And so in doing so, how much can the x variable explain the degree of variation away from the regression line in the outcome variable of interest? And just to review the form of the line of best fit, recall that it is a line, and the line follows an equation of a plus bx. Y hat, and so the symbol you see here over the symbol y is just simply referred to as a hat, and so the y hat is not the raw y score, it is the predicted score from the equation. And so the equation incorporates the raw score along the x-axis, and that's our predictor variable. So that's the measured x value, the observed x value. A is what's called the y-intercept. So if x takes on a value of 0, what will be the value of y? The b coefficient is the slope of the regression line, how steep that line of best fit is on the scatter plot. And so this is the equation of a straight line that will form the basis of the coefficient of determination. So before you move on to interpret and apply the line of best fit, we need to calculate the coefficients. A and B are the coefficients we need to calculate. And so these are the equations to compute the B coefficient and the A coefficient. And so we'll start with the B coefficient. So the B coefficient is the slope, how steep that line is on the scatter plot. And this could take on a positive or a negative value that is going to be dependent upon the R statistic that we had calculated earlier. Recall that the R statistic could be a positive value or it could be a negative value. The magnitude of the slope is going to be determined from the ratio of the standard deviation of the y scores divided by the standard deviation of the x scores. On the right hand side, the coefficient A is the y-intercept, the value of y when x equals 0. So the point at which the line of best fit intercepts or intersects with the y-axis. And so to calculate the A coefficient, we will follow this prescribed equation. And so once again, the y-intercept is the value along y when x equals 0. So recall r is the correlation coefficient, the PPMC value that was computed earlier. Sy, and you'll see Sy in both equations. So Sy is the standard deviation of the raw scores of the outcome or the criterion variable. Sx is the standard deviation of the raw scores of the what we labeled as the predictor variable, and you see that here once again appearing in both equations. And this highlights an earlier approach where when we have the data generated from a research study, we have the raw values. We always want to calculate the descriptive statistics first. In other words, calculate the average and standard deviation as an automatic approach before moving on to any other statistical procedure. Y bar, so the bars is merging a little bit with the Y here in PowerPoint, but Y bar is the average score of the raw Y scores, and X bar is the average scores for the predictor raw scores. And we see that these two values appear in the y-intercept equation. So moving on back to our example of our sets of our two sets of course final grades of 7 students. Once again, just to establish that we have our predictor variable of our raw X scores and our criterion variable, which is our outcome variable that we're trying to predict given the X, given the grades in that first year anthropology course. So at this point, what we want to do is we want to first start with our calculations of the coefficients. So at this point, this would be another good point to pause the video and go through the calculations. For first, we'll go over the B calculation, then we'll go over the A calculation. So presumably, you're restarting the video from your calculations, and we'll start with the slope calculation. So earlier we computed the R value to be a positive 0.98. We did not go through the demonstration, but the standard deviation of the Y scores was found to be 4.42%, and the standard deviation for X is 4.91%. When we work through our calculations, we have a B value of 0.88, and this should be a positive value. Moving on to the calculation of our y-intercept, we see it's a little bit more involved, but we calculate from our descriptive statistics. We had calculated a y bar value of 82.71 of this column here. We have, when we subtract the product of R, which is 0.98, so this is a positive 0.98. The subtraction is part of the equation. And we have the same ratio we saw in the slope calculation, the 4.42 divided by 4.91, and we multiply that by the average scores of the first year course, which is 52.86. So we performed the multiplications here first, and then we do the subtraction with 82.71, and we end up with a value of 36.08, and we then substitute those to arrive at a final model or a final equation of y hat equals 36.08 plus 0.88x. And so moving forward, we can then predict the outcome of the score in the second year anthropology course given the final score in the first year anthropology course. So in doing so, we'll take our equation of 36.08 plus 0.88x, And so, for example, let's suppose that following this study, a student achieves a grade of 52% in the first year course. So another good time to pause the video, and the question that we're going to leave you with here is predict this student's grade in the second year anthropology course. So pause the video now, run through the calculations, and then restart the video for the answer. Okay, welcome back. And so we start with our base equation that we determined. We then enter the 52% for x, and we substitute that value. We perform the multiplication between 52 and 0.88 first, adhering to the order of operations for arithmetic, and we have a final predicted score of 81.84%. What we're doing here is we're predicting this student's final grade in the second anthropology course before the student even registers for that second year anthropology course, given their first year score. And so the predicted grade of 81.84% is contrasted with perhaps the actual grade of 83%. So 81.84 is what we predicted the student would score before they registered. Upon completion of the course, we might find that the student scored an actual grade of 83%. So it's not going to be a perfect prediction. There's going to be a difference. And the difference is what we refer to as the residual. It is the difference between an actual score and the predicted score. And the residual is illustrated here, will be illustrated on this graph. A little bit of a different example here, where we are examining if age can predict blood pressure. And in this case, age, as you can see here, is the predictor variable on X. Blood pressure is the criterion variable, our outcome of interest, along Y. And so here we see a raw data point. So that's a raw score from one participant. So from this one participant, we track their age, and we obtained a blood pressure measurement. The residual is the difference between the actual score and the score that would reside on the line of best fit. So the dot here is what we measure from the person. The point on the line corresponding to that person's age is what we predict from the equation. So once again here, the residual, the difference between those two measures, gives us an estimate of the error, the variability in our prediction, knowing that our predictions are never going to be perfect. So y hat, once again, is the predicted value along the line of best fit. We do not observe this value. We predict this value from the equation, but y is that actual predicted score from the equation. So going back to our example of first year anthropology grades, our second year anthropology grades, remember the first step we do is we generate a scatter plot, and we take a look at the data. We come up with a subjective impression of what we observe here. And we can see that we do have this upward trend, this positive direction, that as anthropology 1150 grade goes up, so does anthropology 2230 grade. But then we ask the question is how accurate would be this growth, this positive relationship. And so at this point, we generate a line of best fit. And we see here that this line of best fit follows a similar value that we had computed by hand. This was a value that was calculated using Microsoft Excel, and the R-squared value is 0.9589. Now, notice that this is considerably different than the R value that we calculated at 0.98. The difference is that we took the 0.98, we squared it, and we get the coefficient of determination of 0.9589. And so what we are left to do here is to get an estimate of how much error we can expect in predicting the outcome of the second year anthropology course, knowing that we do have a very strong correlation and a strong coefficient of determination here, that the maximum value can only be 1.0 or 100%, but we see that the raw scores do not fit perfectly on the line of best fit, but they're not located that far either vertically. And so the question here is, can we be specific in estimating the expected variability? And we can, and we'll do that in the next video.